So this is our second video on transformations of functions, and I think I misspoke a little bit at the end of the last video. I said it was time for the exercise, but we weren't to the exercises yet. And in fact, I should have just summed up what happened with example 1 and 2. So let's just think again just briefly about example 1 and example 2. G of x squared plus 2 gave us the graph of f shifted vertically upward 2 units, right? And in our second example, g of x equals absolute value of x minus 4 gave us the graph of the function f shifted vertically down 4 units. So we want to make this observation in the box that for any constant d, we can shift the graph of y equals f of x vertically to obtain the graph of y equals f of x plus d. If we had a constant on, we move vertically. We shift the graph either up or down. We move upward d units if d is positive, downward if d is negative. Now let's go ahead and start talking about examples. We're going to do examples 3 and 4, and then we're going to do an exercise. So we're going to make another kind of comparison in example 3, where again we're just sort of adding or subtracting a constant in the expression for a function, but we're going to see that in example 3 something a little bit different happens. And in example 3 we're comparing f of x equals x squared to g of x equals x minus 3 squared, where the minus 3 is inside parentheses. Now think about that change of position. And I already went ahead and wrote down the table for f because we just calculated that in example 1. And I also have the graph of f drawn here already for us. We're just going to start talking about this example G. And now I can pick the same values of x and plug in. Really, I can plug in any values of all. But I'm going to try to point us in a certain direction here. So I'm actually going to start out by plugging in 0 for x into the function g. So I get 0 minus 3 squared, which is minus 3 squared, or 9. And then I'm going to do 1. So I get 1 minus 3 squared, which is negative 2 squared, or positive 4. And then 2 minus 3 squared is negative 1 squared, which is positive 1. 3 minus 3 squared is 0 squared, which is 0. 4 minus 3 squared is 1 squared, which is 1. 5 minus 3 squared is going to be 2 squared, or 4. 6 minus 3 squared is 3 squared, which is 9. Now, it really doesn't matter which x values I pick, okay? But I pick these in a certain way because just notice that the y values we have in my table for f of x are the same as the y values we have in the table for g, 9, 4, 1, 0, 1. And now, maybe before we draw any conclusions, let's just go ahead and plot these points down below on the graph grid. So I know I'm covering up some of the points, but I can see them here. We have 0, 9. We have 1, 4, 2, 1, 3, 0, 4, 1, 5, 4, correct, and 6. 6 would be the next space, so 4, 5, 6, 7, 8, 9 right here. And I think I want you to see these are kind of in the same arrangement as we had before, so I think we can see the graph would be a U shape sort of in this position. And So here's our graph of G. So what's kind of interesting is what's different about this example is that we didn't shift up or down, we shifted sideways, right? And the thing that is a little bit surprising to people usually is to get from the graph of F to the graph of G, we have to shift the graph of F 3 units to the right in the positive direction to get the graph of G. So one issue is that, yes, the two graphs are related. We can shift F to get the graph of G, but we don't shift up and down vertically like we did in example 1 and 2. We shift sideways here. So that's part of the difference caused by adding a number or subtracting a number inside the parentheses of the function as opposed to outside. And also what's surprising is, even though the expression for G involves, subtracting 3, we actually shift 3 units to the right. And, why is that going on? What's going on here? We can kind of see what's going on from these values that I chose in my table. And if you go across and you compare, you could say to get the same y values, so the x values are different, but I get the same y values, 9, 4, 1, 0, 9, 4, 1, 0, etc., comma, the x values need to be increased by 3. So notice, if you increase negative 3 by 3, you get 0. If you increase negative 2 by 3, you get 1. All the way down the line, if you increase 3 by 3, you get 6. 2 by 3, you get 5. So to me, this is the reason why we actually shift to the right. It's this increase which is giving us the positive 3 movement to the right, even though the formula for G has a minus sign in it. So in example 3, here was our data, our two functions, and then the observation is we actually have to shift F 3 units to the right to get the graph of G. Now let's look at one more example. So example 4 involves absolute value, and I already put in the table of values for F because we just did that in example 2. And I also graphed F down below because we, again, save us a little bit of time, we just went through that. But now we need some information about G. And really, I could pick any values of X at all and just plot points and I'd figure out that graph of G. But just to help us understand what's going on, I'm setting this up in a certain way. I'm actually going to start with x equals negative 5 here and plug into the function G. So I get the absolute value of negative 5 plus 2 is the absolute value of negative 3 is 3. If I plug in negative 4, I get the absolute value of negative 4 plus 2, which is the absolute negative 2 is 2. If I take negative 3, the absolute value of negative 3 plus 2 is the absolute value of negative 1 is 1. And I don't know if you see the pattern yet, but I'm doing something similar to what I did in the previous exercise. I'm trying to get the same y values, the same outputs. I get 3, 2, 1 here. I'm getting 3, 2, 1 here. So you don't have to know how to do this, all right? That's not essential. You may see it, but if you don't, that's fine. At negative 2, I get negative 2 plus 2 is 0. Absolute value of 0 is 0. At negative 1, I get the absolute value of negative 1 plus 2 is the absolute value of 1, which is 1. At 0, I get the absolute value of 0 plus 2, which is the absolute value of 2, which is 2. And at 1, I get the absolute value of 1 plus 2, which is the absolute value of 3, or 3. So let's go ahead and plot these points now. I have negative 5, 3. And I know you can't see them, but I can. Negative 4, 2. Negative 3, 1. Negative 2, 0. And negative 1, 1. 0, 2. 1, 3. So I can see that absolute value V forming, but it's shifted off to the side here. There's one piece. And if you plotted more points, you should see all this confirmed. Or if you plotted totally different points, you should see this shape confirmed. So here's my graph of G. And the interesting observation is, again, we don't shift up or down. We're shifting the graph of F sideways. And we see that we have to actually, we want to shift F 2 units to the left, which is that away, to get the graph of G. And it's a little bit counterintuitive here, because in the formula for G we see a plus 2. It's inside the absolute value bars, and yet we don't move in a positive direction. We actually shift the graph of F in a negative direction to get the graph of G. And in my table, you can kind of see why that's true. At least I'm trying to make a point here. And I would say to get the same y values in the table for G, the x values need to be decreased by 2. So 2 less than negative 3 is negative 5. 2 less than negative 2 is negative 4. And then I get the same y values. So it's really this decrease idea here that's causing the graph of G to be shifted 2 units in the negative direction. Now you got to just memorize this. And it's actually one thing that helps me a lot here, and I'm going to go back to example 3, 2, is to notice the point of the vertex of the x squared parabola is at 0, 0. It's helpful for me to look at this function G and realize if I plug in 3, x equals 3, I'm going to get a y coordinate 0, right? 3 minus 3 squared is 0. So when I plug in 3, I get 0. And that helps me see that on the graph of G, that vertex is going to be over here at 3, 0, which is actually 3 units to the right of the graph of F. And in our other example, the point on the absolute value graph of F is at 0, 0, right? And for the function G, if we want to know where the point is going to be, it's not when we plug in 0, it's when we plug in a number that gives us 0, and that's going to be negative 2. Negative 2 plus 2 is, absolute value of that is 0. So the point on the graph is going to occur here, where x is negative 2, and that helps me, if I can see that the point is going to be at negative 2, that helps me see that I've shifted to the left, right, by 2 units. All right, so let's just sum up this idea back in our handout with this statement about horizontal shift. So for any constant c, we shift the graph of y equals f of x horizontally to obtain a graph of y equals f of x plus c. So the difference here is the plus c is inside the parentheses of the function. With our vertical shift, the plus d was outside the expression of the function. And horizontally means sideways, to the left or to the right. Move to the left, c units if c is positive. Move to the right if c is negative. That's kind of counterintuitive, right? So we kind of have to say, careful with this one. And it is sort of weird that positive means up for a vertical shift, negative down. But for a horizontal shift, positive means to the left in the negative direction, and minus means to the right. So now we're ready for some exercises, and we're gonna do that in the next video.